Continuing on our discussion of boiler operation from the previous module, we'll now look at various aspects of boiler control. This will include an examination of that very important feature of boiler operation, boiler water control and conditioning. We'll also discuss environmental factors and control of boiler emissions and effluents. But first, let's take a look at the control devices that permit the operator to run the boiler as efficiently as possible while responding to changes in load demand. We have already studied monitoring equipment, both the traditional control panel and the modern operator's console. In either case, the operator is able to stop and start equipment and make adjustments remotely, that is, from his central operating position. The operator can also manually adjust all of the major operating parameters, such as fuel input, combustion air, feed water flow, steam temperature, and so on. Of course, it's almost impossible to simultaneously control all of the many variables manually. Indeed, it is essential that the major operating variables be controlled automatically. Modern automatic control systems have been developed to a high degree of precision and can provide excellent results in maintaining a high level of efficiency, reliability, and safety. This schematic shows the essential components of a control loop. They are the sensor, transmitter, controller, and actuator. The sensor measures the operating parameter that is being controlled, such as pressure, temperature, flow, or level. This information is then fed into the transmitter, which prepares the signal for transfer to the controller. Older installations still use compressed air as the signal medium. Typically, the pressure of the pneumatic signal will vary between 5 and 30 psi, depending upon the value to be transmitted. Another method for information transfer is via electrical signals, with the transmitter output being adjusted by millivolts or milliamps. These pneumatic or electric signals are known as analog signals. In modern installations, a transmitter produces digital signals for transfer to the computer or central processing unit in the control room. The digital signals have the advantage of being faster and being able to transmit a higher volume of information. Another advantage of the digital control system is its ability to continuously check incoming readings for accuracy and abnormal indications. It does this by comparing multiple readings, computing averages and implied values, so that any obviously incorrect signal is discarded before it can bring about faulty positioning of the auto controls. So returning to our schematic, the sensor signal is fed into the controller, where it is compared with a set point established by the operator. Where any deviation is present, the controller sends an action signal to the actuator to make corrections. The actuator is really the power device in the system, converting small analog or digital signals into mechanical movement. For example, to adjust the fan dampers or to open the feed water control valve. The actuators generally are motivated by compressed air or precisely controlled electric motors and positioners. Even when we're operating the system manually, the actuators are still required to adjust equipment position. In fact, the changeover from automatic to manual control merely allows the operator to provide the driving signal to the actuator and thus enables remote operation. So let's take a look at some typical control circuits. Here we'll simply be looking at the logic of the circuit. The actual control system may be pneumatic, electrical, or digital, but the logic of the operation is the same. Here we see a very basic combustion control scheme for controlling boiler main steam pressure. The actual measured pressure is compared in the master controller with the selected set point. Any deviation causes a correction signal to be sent to the fuel supply actuator and the combustion air actuator. During load changes, the signals are biased so that sufficient combustion air is always available to avoid the potential formation of a rich, explosive mixture in the furnace. For example, during a load increase, the airflow is increased before fuel is increased. The reverse applies during a load decrease. Either of the actuators can be switched from automatic to manual operation if required. An additional control allows the operator to set the desired fuel-air ratio. Experience proves that more excess air is required at low loads to maintain stable combustion. One disadvantage of this simple system is that it must wait for the pressure to actually fall before commencing a corrective action. And even then, some more delay is experienced in mechanically changing the airflow and fuel supply. Yet further delay is encountered before the increased combustion brings about the desired rise in pressure. The cumulative delay from this control system results in a fluctuating steam pressure. This situation can be vastly improved by adding a second element to the control system. That is, by measuring the steam flow from the boiler and using this as an anticipatory signal. We know that increased steam flow from the boiler will result in a falling steam pressure within a time period of about 10 or 15 seconds. However, by applying the steam flow signal to the master controller, the corrective action is started in advance, and so provides increased combustion at about the same time as the pressure begins to fall. The actual resultant pressure then trims the controller settings. A further improvement to the system may be obtained by connecting the oxygen analyzer signal to automatically adjust the fuel-air ratio. This acts as a trimming device to precisely control the combustion air and bring the excess oxygen in the flue gas to the desired set point. Auto control of induced draft, where fitted, is not usually considered part of the combustion control system, as it is operated by a separate, dedicated control loop. The controlling parameter is measurement of furnace pressure, that is, negative pressure. The controller is set to maintain about minus 0.5 inches water gauge in the furnace, and it achieves this by adjustment of the ID fan dampers. Steam temperature control is also independent of the combustion control system. Final and reheat steam temperatures are measured and processed through a controller to actuate one or more attemperating devices, such as adjusting the flow of de-superheating water, adjusting the tilt of the burners, adjusting the flow of gas recirculation. This last technique provides the same effect as firing with increased excess air, but without the increased heat loss up the chimney. The recirculating gas merely circulates in a closed loop, while increasing the mass of gas flow across the superheater tubes, with consequent increase in main steam and reheat temperatures. Now, there are many other arrangements of combustion control systems with increasing degrees of complexity and sophistication. You must make sure to thoroughly learn your own system. Another multi-element control system that is vitally important is the boiler feed water control system. The three elements include the actual level of water in the drum, the steam flow out from the boiler, the feed water flow into the boiler. In this arrangement, the level signal tries to adjust the feed water control valve to maintain a constant level. At the same time, the difference between steam flow out and feed water flow in acts as an anticipatory signal so as to provide anticipatory action on the control valve. In some control systems, the set point value of desired water level is automatically adjusted with load, that is, steam flow out of the boiler. At high load, the target level is maintained slightly higher in anticipation of a possible load rejection, with consequent rapid fall in level due to shrinkage. Conversely, at low load, the set point is adjusted to maintain a slightly lower level in the drum, in this case anticipating the possibility of a sudden increase in steam demand, with resultant increase in water level. Another refinement to the feed water control system may be made to the mode of measuring water level. This measurement in inches or centimeters is usually inferred from the pressure indicated at the bottom of the column of water. The problem with this technique is that the density of water in the drum changes with variation in saturation temperature, and this depends upon pressure. In order to improve accuracy, the drum level measurement is corrected for pressure variation by adding a pressure signal to the computation. Yet further refinements may be made to the water level control system, such as steam temperature compensation to provide more accurate measurement of steam flow, compensation for blowdown and soot-blowing steam flow when comparing output steam flow to input feedwater flow. You must make sure to thoroughly learn the automatic control systems installed on your boilers. One very important feature of any control system is that it must provide smooth transfer from automatic to manual operation and vice versa. In most systems, this is achieved by making the alternative selection continuously follow the actual output signals to the actuators. In this case, any switching from automatic to manual, for example, will keep the actuator in the same position till further change is made. Our discussion here of automatic boiler controls has centered around modulating control systems, which continuously adjust fuel, air, feed water, etc., to maintain the desired operating parameters. The actual on-off actions for placing burners in service and monitoring for safe combustion conditions are carried out by the burner management system, as discussed in the previous module. Well, at this point, it's time for us to take a break. We'll come back and talk about boiler water control and conditioning. For now, please switch off the tape and thoroughly review this material in your workbook. When we're speaking of water control here, we're referring not to the water level control, but rather to the quality of water which is contained in the boiler. We already know that a special water treatment plant, including demineralizers and other equipment, is installed in order to ensure that water which is fed into the boiler is super pure. Additionally, certain chemicals are injected into the boiler drum to further control the chemical condition of the boiler water. So what is it exactly that we are protecting the boiler against? What are the problems that can arise as a result of feeding impure water into the boiler? Well, the principal problems arising from poor water conditioning are the formation of scale and deposits inside boiler tubes, the carryover of water with the steam, internal corrosion causing wastage of boiler tubes. Let's take a closer look at each of these items. First, the problem of scale. As much as we try to provide perfectly pure water to the boiler, it is inevitable that some small quantity of contaminants do get through and concentrate in the boiler water as more and more steam is evaporated. Remember, as water evaporates into steam, the solids contained in the water remain behind, and this concentration increases as more and more steam evaporates. This is the situation which occurs in the boiler. Generally speaking, the contaminants consist of magnesium and calcium salts, which are dissolved in the water and contribute to hardness, silica, the products of corrosion of the boiler itself and the feed water system, mainly iron and copper. At high temperatures, such as encountered in boiler water, and above a certain concentration, these solid materials precipitate out of solution and deposit on the inside of the tube wall. This deposit then forms an extremely hard scale that cannot be removed by the flow of water. The scale acts as a partial insulator of heat and so prevents adequate cooling of the boiler tube by the flow of water passing through the tube. The result is that the temperature of the tube wall metal rises significantly, and in certain zones of the boiler where the radiant heat transfer is at its highest, overheating of the boiler tube metal takes place. The eventual result of this is a failure of the metallic structure with consequent rupture of the tube. Where boiler water contains a high concentration of solids, you should expect frequent tube failures with the resultant need to take the boiler out of service for repairs. In order to prevent this problem as far as possible, limits are established on the allowable concentration of solids that may be contained in the boiler water. This table indicates limits for both dissolved solids and suspended solids. The problem of scaling is aggravated at higher steam pressure because of the higher saturation temperature of the water. Therefore, as we see here, the permitted limit of concentration is much lower when the boiler operates at higher steam pressure. But how can we reduce the concentration of solids? Well, one method is by continuous blowdown. That is, a regulated quantity of water discharged from the bottom of the drum to waste. A control valve is fitted to allow us to regulate the quantity of continuous blowdown. But how can this reduce the concentration of solids in the boiler water? Well, remember, the blowdown water may contain 500 parts per million of solids, and this is replaced by boiler feed water, which contains perhaps 5 ppm. The result then is dilution, with the consequent reduction in total solids concentration. As the blowdown water is at relatively high temperature, between 400 and 500 degrees Fahrenheit, it is discharged into a blowdown tank. This permits some of the high temperature water to flash off into steam and to be vented to atmosphere. The remaining water is then discharged to waste. Of course, there are some losses involved in discharging blowdown to waste. First, there is the loss of heat contained in the water, and secondly, the loss of water itself with consequent increase in makeup requirements. Actually, the best way of keeping the solids content of boiler water at a low level is by maintaining control over boiler feed water and its makeup. The actual limits established for boiler feed water contaminants depend upon the particular boiler operating pressure and temperature and operating regime. However, we would typically expect to find the following analysis of boiler feed water and makeup. These concentrations are given in parts per million ppm. Total dissolved solids are less than 5 ppm. Silica is below 0.15 ppm. Alkalinity is 2 ppm or less. Hardness, as calcium carbonate, is at 2 ppm or less. Feed water may also contain some products of corrosion from the condensate and feed water system. This usually consists of particles of iron and copper which are dissolved into the water stream from pipework and heat exchangers. All of this material ends up in the boiler and increases the concentration of solids. The target limit for copper and iron in feed water is usually established at 10 parts per billion or less. We'll be talking more about corrosion later in this module. Even with all of these precautions and controls, there is still a tendency for the concentration of solids to build up in the boiler water. For this reason, an attempt is made to prevent scale formation by injecting a chemical dispersant such as phosphate into the boiler water. This is usually added at the boiler drum, so a high-pressure pump is required. Phosphate has the effect of keeping the magnesium and calcium precipitate in suspension by dispersing the solid particles throughout the water. The result then is that instead of forming a hard scale, the solids remain as a slurry to be discharged from the boiler through the continuous blowdown line. The addition of trisodium or disodium phosphate to the boiler water does have some negative aspects. For one, it adds yet further solids to the water. In addition to this, it will affect the pH value of the water, and this may aggravate corrosion. We'll discuss this later. Another problem associated with high solids content in boiler water is carryover. The effect of the dissolved and suspended solids is to increase foaming on the surface of the water in the drum. This in turn leads to carryover of water with the steam. Carryover may also be caused by fluctuating water level in the drum or a persistent high water level. High alkalinity in the boiler water may also contribute to carryover. The result is that water is carried on through the superheater, possibly depositing solids and forming scale on the inside of the superheater tubes. The water droplets may also pass along with the steam into the turbine. Here, the water and solids material can cause considerable damage when striking the rapidly rotating turbine blades. We mentioned that silica may be one of the contaminants contained in the boiler water.